Howdy, calculus people. So today in class, we would have gone over optimization. So this is topic 5.1 or 510 and 511. So last section of this unit. So after this, that means that it's going to be review test time. So kind of keep that in mind over the next little bit. So timeline is you can take the notes on optimization today from this video, and then tomorrow would be your off day. And so you'll work on your optimization skill builder. And then Friday is just going to be time to work on the test review, and then you would test when you come in on Tuesday. So that's the current timeline. If it changes, I'll let you know, and we'll update that accordingly. Same as before, if there's just a regular NTI day tomorrow, I'll hold a Google Meet and you can come and ask questions, things like that. All right. Email me if you need anything. Please email me. All right. Okay. So optimization is an application of the derivative, and it's kind of the last application of the derivative that we're going to talk about. And so when you optimize something, you're finding like the best possible situation. So for example, the first question that we're going to do is we're going to talk about a box. And the box has to meet some requirements. So we have so much material that we want to invest into the box because material costs money, but we want the box to have a lot of volume on the inside. And so what shape box should we have? So like for example, if we're working with a bunch of boxes, these are all boxes that have the same kind of surface area going on, but they all have different volumes. They're different shapes. And so optimization comes in handy in a lot of manufacturing type situations, jobs, things like that. And so we're just going to touch the surface on some optimization. Really what we're looking for are maximum and minimum values. And so that's why it's a strong application to the derivative, because the derivative helps us find relative maxes and relative mins. And so that's really what we're going to be using here today. All right, so let's get into this first example. It says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions should the box be in order to produce a maximum volume? So we're going to maximize this problem. Now, we're looking for a max volume. And so when we talk about a max volume, we actually have to talk about the volume of this box. And so we're just going to use the dimensions that they give here. It did say a square base, so I know it doesn't look very square right now, but x by x would be the square base, and then height of h. So the volume of this box is technically x squared times the height. Now the information that they give us is about the surface area, and the surface area is 108 square inches. So we are going to maximize this equation, but in order to do that, we're going to have a secondary equation that we're going to use to help us maximize. So our surface area equation would be, if you remember surface area, it's just all the areas of the faces added together. And one important thing to note that this box has a open top. So this piece right here is not included in the surface area. That's open. All right, so the bottom of this box would be x by x, which is x squared, and there's only one bottom. The front of this box, what you see here, is x times h. The side of the box is also x times h. The back of the box would be x times h, and the side over here would be x times h. So there's actually 4 of those, 4 plus 4x h. And it tells us that that has to equal 108. That's the surface area. So what we're going to do here is we're going to solve this equation for h, and we're going to substitute h in. Essentially, we're solving a system of equations. We're kind of doing the beginning steps of solving the system, because once we get this in here into the volume formula, then we'll take its derivative and find the maximum. So I'm going to solve for h. So to solve for h, we would subtract x squared. So this would be 108 minus x squared. And then I would get rid of this 4x in front of it by dividing by 4x. And so what we're going to do is we're going to take that h and we're going to plug it in over here. So my new volume equation is x squared times 108 minus x squared over 4x. And so this equation here in pink is the one that we are going to maximize. This is maximize volume, so we're going to do the volume equation. All right, before we do that though, I actually think before we take the derivative, we can do some simplifying, which is going to make this a little bit nicer. So because there's an x in the denominator, x in the numerator, we can simplify one of those. So it'd be x times 108 minus x squared over 4. And then before I take the derivative, it's actually easier still to go ahead and distribute that x. So then I don't have to use the product rule. So 108 x, we can say that's over 4 minus x cubed over 4. And actually, there's one more thing we can do to simplify, right? 108 divided by 4 is, let me grab my calculator. I think it's 27, but I'm just going to make sure real fast. Yeah, 27. So 27x minus x cubed over 4. All right, so we have our volume equation. We were just simplifying here. And so now we have the simplest volume equation we can work with. And we're going to go ahead and optimize this by taking the derivative. So from here, I'm going to jump over and I'm going to find v prime. All right, because maximum and minimum values happen when the derivative is equal to 0. So we're going to find v prime, set it equal to 0. So 27 minus, this would be what, 3/4 x squared. And we are trying to find where that is equal to 0 because maximums and minimums exist where this is equal to 0. All right, solving, you can either try to factor, you can use the quadratic formula, you can use the square root property here because it's just an x squared. So that's the one I'm going to use. So I'm going to say negative 3/4 x squared equals a negative 27. Subtract that over. Multiply by that negative 4 and the 3, or you can think about it as dividing by negative 3/4. I like to think about it as you're going to multiply by 4 and divide by 3, and you just have to have negative here, right? And that'll get rid of this. And this is actually easier to do the division first. Negative 27 divided by 3 is negative 9. Negative 9 times negative 4 is 36. And then take the square root. X would be plus or minus the square root of 36, which is 6. And so remember what x is. X is the side of the box. It doesn't make sense for x to have a negative value because you can't have negative side lengths. So x is going to be a positive 6. Now we did all that work. Let's make sure we actually answer the question. So the question specifically says, what dimension should the box be in order to produce a box with the maximum volume? So the one side is going to be 6 inches, and the inches are given right here, right? Square inches, so inches. So 6 inches. So the box has to be 6 inches by 6 inches, that's x by x, by the height. And to find the height, you have to plug it in here, go back and find the height, or you can plug in here the 6 and find the height. So that would be 108 minus 36 divided by 24. And so the height is going to be 3 inches. So the dimensions of the box are 6 by 6 by 3. That will give us the max volume and still have a surface area that is 108. So if you look at the possibilities down here, this is the one with the max volume. And I know they kind of already went through and showed you the volume, but you can actually see how that is the max volume. So all of these were possible answers, but the one that does yield the max volume is 6 by 6 by 3. All right, so a little bit about optimization. Most likely, if you see optimization on the test, it's probably going to be in the form of a multiple choice question. And no, they're not necessarily going to ask you to do all this work. The equations might be a little bit simpler. Or they might go ahead and give you really complicated equations and kind of start you down the path and start you somewhere. So we're going to look at these. At the core, it's the same process every time. You're going to have two equations. You're going to have your main equation, which is what your question's about, maximizing volume for this one. So this is like our primary equation. Then you're going to have a secondary equation that has like another condition that you have to meet. And so in this case, we had to meet the surface area condition. You use the surface area, the secondary equation, to help you simplify the primary equation. So you're down to one variable. Take its derivative, set it equal to 0, and solve, and that will automatically give you a maximum/minimum value. Now, the hard part here is how complicated these equations are. So the more complicated the equation, the harder it is because there's more solving involved. All right, so here's just kind of some directions. This is pretty much exactly what I was talking about with primary, secondary equations, setting them up. So you can always go back and read through that. All right, so we're going to work through some more of these examples. So which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So they give us a graph so we can kind of vision what's happening here. 4 minus x squared, it's going to have a y value of 4. And then you can just plug in if you want. You can plug in 1. If you plug in 1, you'll be at 3, right? So if you plug in -1, you're also at 3. Plug in 2, you'll be at 0. -2 also at 0. So here is that graph of that quadratic. And we want to know which points on the quadratic are closest to that point. So the distance from here to here, here to here, or here down here, right? Any points, which one is the shortest distance? So same thing over here. Which one's the shortest distance? So the shortest distance is actually you're going to have a point on this side and a point on this side because this is a symmetric function. It's a parabola. And so, yeah, we're going to be doing some pretty intense algebra going on here. So let's see what we get. All right. For the main thing, our primary equation, is we want to know points that are closest. And so what we're talking about is the distance. So our primary equation is our distance formula. So distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. By the way, the distance formula, it's just the Pythagorean theorem, like distance squared equals your x squared plus y squared, or a squared plus b squared. And so I don't typically have it memorized. I just think of it in terms of the Pythagorean theorem as I'm doing this. All right, so in terms of our secondary equation, we already have it. It is the relationship between x and y on the parabola. And so the nice thing is we just have to work with this equation. This is our primary. The secondary equation was already handed to us, so we didn't have to write it like we did in the first one. And so we're good to go ahead and plug in our values that we need. So we're simplifying our distance equation, and then we'll take its derivative and figure out what number maximizes it, where is the derivative equal to 0. All right, so in terms of x1, x2, all that fun stuff, one of them is going to be 0. That's an x coordinate. And then the other x coordinate we don't know. We're going to try to figure it out. And so I'm going to go ahead and say, well, we're looking for one of the x's. The other x is 0, so we'll plug in x minus 0 squared there. For the y's, we don't know the y coordinate, but we do know the y coordinate in terms of the x coordinate. So we'll have 4 minus x squared there. And then the other y coordinate, minus 2, and that whole thing is squared. And so this will be our distance. All right, let's do a little bit of simplifying with this formula, make it look a little bit nicer if possible. So x minus 0 squared, that's just x squared. 4 minus x squared minus 2 would be 2 minus x squared, and that's squared. And then if you want, you can go ahead and distribute and combine like terms in the inside. Or if you want, you're okay to just go ahead and do the derivative at this point. So I actually just went ahead and did the derivative, and I just used the chain rule to help me out. So that's what we're going to do, because we're going to practice our chain rule. All right. So taking the derivative. So this is what's going to find the closest point. So the minimum distance is what we're finding. So the derivative of a square root is 1 over 2 square roots, right? So on the bottom, I'll have 2 square roots, and inside the square root, nothing will change. Squared. On the top of the square root is going to be the derivative of the inside. So just going in order, the derivative of x squared is 2x plus, and then the derivative of this mess right here. So this is where you use the chain rule a bunch. So technically we've already used the chain rule, but we're going to continue to use it. So the power of 2 comes down, so it'd be 2 times 2 minus x squared, and then times by the derivative of the inside, well, that'd be 0 minus 2x, so a minus 2x. And this is the equation that we're going to try to solve. Where is it equal to 0? It could also potentially be undefined, right? You always kind of have to keep that in mind. Let's talk about the undefined. Undefined happens when the denominator would be equal to 0. Look at what's happening here. You have an x squared, and then you have some number also squared, and those two numbers are going to be added together. So if you square a number and square another number and add them, both of the squared numbers have to be positive. And since we're adding them together, it's still positive. So there is no way that that denominator can be equal to 0. So we can rule that out. So that means we're just looking for where the numerator is equal to 0. So 2x, then I'm going to go ahead and multiply these two together, make it a little bit easier. So minus 4x, 2 minus x squared. Where is that equal to 0? So continuing to solve, continuing to distribute, we would have minus 8x, and then plus 4x cubed equals 0. Combine like terms, that would be minus 6x plus 4x cubed equals 0. There's a GCF here that will help me solve. I can take out a negative 2x. So that would leave me with 3 minus 2x squared equal to 0. All right, and so my options here are x equals 0 from the first piece, the 2 or the minus 2x, and then solving this, 3 minus 2x squared, where does that equal to 0? Well, subtract 3, divide by 2, so that's x squared equals 3 halves. And then take the square root. When you take the square root, you include plus or minus, so plus or minus the square root of 3 over 2. So we have 3 points at x equals 0, at plus or minus square root of 3 over 2. And so checking out which one's the closest, you have to kind of think, right, we got this one, and we got these ones as well. And so how do we know which ones are exactly the closest? Because this might be closer, that might be closer. Well, plug them in and figure out their y value, and then you can actually like calculate the distance there. All right, I will let you know that I'm kind of running out of space. Wish I had more space here. So if you plug in, let's go ahead and plug in this plus or minus square root of 3 over 2. If you plug that in, you would have 4 minus the square root of 3 over 2 squared. So that would be 4 minus 3 over 2. And 4 minus 3 halves is 5 halves, right? 4 minus 3 halves is 5 halves. So these coordinate points would be at square root of 3 over 2, 5 halves, and negative square root of 3 over 2, 5 halves. And then if you plugged in the other one, 0, your other x that we found, you would have 4 minus 0 squared, which is just 4. And so you have to check the distance between this point and this point right here. And so if you just look at your graph between 0, 4 and 0, 2, that's going to be a distance of 2. And if you look here, even at any of these, this is not 2. So this is definitely not the right answer. That has a distance of 2 there. And it's very obvious that this is not 2 units apart, right? Because it's the inside of 1 square, so it would be just over 1. So these two are going to be your solution. All right, so here's the next one. A rectangular page is to contain 24 square inches of print. If the whole thing's 24 square inches, they're talking about an area there, right? All right, and it says the margins at the top and the bottom of the page are to be 1.5 inches. That's what you see here and here. And the margins on the left and right are to be 1 inch and 1 inch, and that's what you see here. What should the dimensions of the page be so that the least amount of paper is used? All right, so we need a couple equations. So the first equation that we're going to use is going to talk about the 24 square inches of print. And the print is just this section. So that's an area, but it's not the full area of the page. It's just the area of the print. And so if you check out the area, it's x for the height and y for the width. So we know that x times y has to be equal to 24. That meets this condition there of the area of the print, 24 square inches. And then the other equation is based off of our question. What should the dimensions of the page be? So the whole page is going to be another area, but we want to know the entire thing, and that would be height times width as well. And so this is not x times y because that's just the print area. This is actually the whole side is x plus 1 inch, 1.5 inches, 1.5 inches, so 3 inches. And then on this side, that would be y plus 1 inch and 1 inch, which is 2 inches. So our full area is x plus 3 times y plus 2. All right, and once you have your primary equation, this is going to be the one that we're going to maximize or minimize. And then you have your secondary equation, which is the one that we're going to plug in to help us solve here. Then you're ready to go ahead and do some simplifying and take your derivative. So I'm going to solve for x. So that would be 24 over y. Actually, I lied. I'm going to solve for y. I'd rather be working with x's because that's what we're most used to. So y would be 24 over x. So in our area equation here, we would have x plus 3. And then the y will be replaced with 24 over x plus 2. All right, and you can either take the derivative right now and use the product rule, or you could go ahead and distribute first and then just use power rules. I think it might be easier to not product rule this. I think product rule might make it look a little crazy. So let's go ahead and distribute first before we do anything. So x times 24 over x is just 24. X times 2 would be plus 2x. Multiply here, you'd have 3 times 24 over x, which 3 times 24 is 72 over x. And then last we would have 2 times 3, which is 6. And then technically you can combine the 24 and the 6 together for 30 plus 2x plus 72 over x. All right, and so now we're ready to go ahead and take the derivative. So the constant's going to go to 0. This 2x will be 2, and then plus, this is, if you need to go back and rewrite it, x to the negative first, right? So this would be bring down the power, so our plus would actually be a minus 72, and then subtract, so x minus to the minus second. So you could think about this as 2 minus 72 over x squared. And we want to know where that is equal to 0. So we need to solve this equation. All right, so moving the 2 over would be negative 72 over x squared, equals -2. The negatives will cancel themselves out or simplify themselves out, sorry. And then to solve, you can multiply up. So 72 equals 2x squared. Divide by 2. X squared is 36. Take the square root. So x is plus or minus the square root of 36, which is 6. And in terms of the length of a paper, having a negative doesn't make any sense. So just positive 6. So if x is positive 6 inches because of this information right here, then what is y? Well, just 6 times what is 24? That is 4. So 6 inches and 4 inches are the x and the y, right? This is x and y, but that's not technically the paper yet, is it? So I found x and I found y. So technically for the paper, you have to do x plus 3, so 9 inches for the length here, and then y plus 2 by 6 inches for the full length. So this is the actual paper, where this was just x and y, which was just the print area. All right. So kind of the new things that we're going to see is setting up the equations, and then you kind of substitute, right? That's not necessarily a new idea to substitute one in, but then simplifying, taking the derivative, we've done all of that stuff before, and then kind of analyzing what's happening at the end, what you have. So some of these can be a lot easier than others. They get more and more complicated as the equations get more and more complicated. All right, so 2 more examples. I'm going to just do this first one with you, and then I'll take a picture and upload number 5. You can try on your own and then come back and take a look at the picture and see what you come up with. But these are on a closed interval, and so because they're on a closed interval, that means that you also have to pay attention if you're going to find max and minimums to the endpoints. So whenever you're talking about max and mins on a closed interval, always look at the endpoints as well. So when we're done with this question, we're going to make ourselves a table, and we're going to have our endpoints as well as any of the derivatives equal to 0 values, critical points essentially that we found along the way. All right, so let's go ahead and figure out what's going on here. We have 2 posts. One's 12 feet high, so that's what we see here. The other is 28 feet high, and they're 30 feet apart. They are to be steadied by 2 wires attached to a single stake running from ground level to the top of each post. So what they're talking about is this point right here. Here's the stake in the ground, and there's a wire running here and a wire running here. And it says, where should the stake be placed to use the least amount of wire? So where do I put this stake on the ground so that this wire plus this wire is the least amount? So your endpoints, if there are 30 feet between them, the first option is that you could put it at the bottom of this post and run down and then up. The other endpoint would be over here if you put it at the bottom of that post. So that would be 30 feet. And you could go down and then up. And so here's our 2 endpoints that we also have to pay attention to. And then we're going to find a minimum point in here as well. And we're going to calculate how much wire we would need for each one. All right, so let's go ahead and write some equations. Well, we know that the wire, the least amount of wire, so the length of the wire is going to be W plus Z. So that is actually given to us here. So our primary equation, the length of the wire is W plus Z. All right, and so W plus Z, that actually gives us, we have what, 3 variables we're working with? And so what we're going to do is we're going to go ahead and write a secondary equation for Y in terms of X, and then we're going to write an equation for Z also in terms of X. And so you should be seeing that there's 2 right triangles here. So you can use the Pythagorean theorem. So one of the equations is x squared plus 12 squared, so plus 144, equals y squared. The other equation is based off of z, so we would have 30 minus x, that whole thing squared, plus 28 squared. I'm going to go ahead and calculate that right now. Maybe my calculator, hold on. 28 squared. That is 784. And that's going to be equal to z squared. And so I have two secondary equations that I'm going to plug in for my primary equation so that everything will be in terms of x. All right, one more thing. This is y, this is z, this is y squared and z squared. So when you plug them in, you're going to have to put them in square roots, right? So here's our primary equation. W equals, that'll be the square root of x squared plus 144. And then plus z, so that's going to be the square root of 30 minus x squared plus 784. And so this is actually, in my opinion, some of the trickiest parts, is writing all the equations, substituting them in, getting everything set up so that you have your equation that you need to maximize or minimize ready to go. All right. The other tricky part of this could be some algebra. So now that we have our primary equation, all in terms of x, we're going to take its derivative. So the derivative of a square root is 1 over 2 square roots. And then times by the inside of the square root, so that'll go in the top. So 2x will be in the top instead of the 1. And then actually, if you want, you can go ahead and get fancy and simplify the 2's, right? So simplify to just x over the square root of x squared plus 144. And then plus this square root, so it'll be 1 over 2 square roots, 30 minus x squared plus 784. All right, and so simplifying or taking the derivative of the inside of that would be 2 times 30 minus x, so the power would come down, and then times the derivative of the inside of that, so it would make it a negative, and then this derivative is 0, so that would be our numerator. And then once again, you could get rid of the 2's, but leave the negative, right? So just working on your derivative rules there and simplifying. All right, and we need to figure out where this is equal to 0. And that looks like a lot of fun to try to figure out where it's equal to 0. So actually, this is a calculator-based question. So you can always throw this equation here in a graphing calculator and figure out where it crosses the x-axis. So you can use Desmos to do that, or if you have a graphing calculator app or something like that, you can go check those things out. So I actually have a graphing calculator app on my phone. So I'm just going to show you. This is a TI-84, so it would be very similar to the ones that you have in class. So in your y equals, you clear out whatever's in there, put in your fraction, x over square root x squared plus 144. And then plus, we have another fraction. A little bit more. And I'm going to distribute that negative. So negative 30 plus x. And then square root 30 minus x squared plus 784. Didn't even get an x in here. What was I doing? There we go, 30 minus x squared. Before I graph this, because it might take it a few moments, I'm just going to check to make sure that I have everything looking good. Okay. So graphing. And we're going to figure out where does this function equal 0 at. And so based off of this, it looks like somewhere right in here, right? So you can always go second calc and calculate the 0, and then go over along your graph. So it always says left bound, so somewhere for sure on the left of it, and then somewhere for sure on the right. So I'm just going to go to the very end here because I'm pretty sure it's already crossed. My guess is, no, somewhere really close to 9. So let's see. So it says the 0 is actually at 9. So without having to do any algebra there, x equals 0 is, 0, 9. X equals 9 will make that equation equal to 0. So we're going to go over to our table, and we have 3 values that could be the minimum amount of wire, 0, 9, and 30. And so what we're going to do is we're actually going to figure out how much wire will go in. And you can use this equation. This is the length of your wire. And so plug in 0, plug in 9, plug in 30, and decide which one is the minimum. So square root, we'll have 0 squared plus 144, and then plus square root 30 minus 0 squared. I know I could be simplifying some of this in my head, but that's okay. Oops, accidentally took it out of the square root. That's not good. Plus 784. So if you put the rope or the stake here at 0, you're going to need 53.037 feet of rope. And so, why did I do that? What am I doing? It goes here, right? 53.037 feet of rope. So to go down to 0 and all the way up, 53.037. So we're going to do the same calculation now, but we're going to use 9. I'm going to change that 0 there to a 9. And I'm going to change this one to an 81 because that's 9 squared. So at 9 feet over, it'll be 50 feet of rope. So 50 feet to go from here to here if this is 9 feet away. And last but not least, putting in 30 because that's what it'll be at the other end. This will be 30 squared. There we go. 30 squared. That would be 60.311 feet of rope or wire. And so the minimum amount of wire is if it's at 9 feet. So whenever you have this like closed interval, you do have to check your endpoints as well. And so even though at 0 we were super close, it was 3 feet shorter of wire to put it at 9 feet. So our final answer here, we would say that you put the wire 9 feet from the 12-foot pole. So this is 9, x is 9, so it's 9 feet from the pole that's 12 foot high. And I specifically said just not 9 feet because in terms of the context of the problem, 9 feet from where? Was it this pole or this pole? So when I said my answer, I was very clear, 9 feet from this pole will make it the minimum amount of wire. So I'll post, you can try this last one. It's kind of tricky because we're talking about squares and circles. I will let you know that you do have to make a table and check your endpoints, all that fun stuff. But I'll post a picture of it. Let's see how far you can get. And then if you want to start on your skill builder today, that's fine. The skill builder, it's 5.1, 5.3 optimization. And there are quite a few problems in here. Some of them are similar to ones that we've seen before. Some of them are slightly different. And so there's actually 17 of them. So let's go ahead and tomorrow, so this will be your off day assignment, so your Monday assignment. So tomorrow you can have the entire day, like there won't be any more new notes or anything to work on that. And I'll hold a Google Meet tomorrow, so if you have questions, we can go over those. So yeah, that's all I got for you. Hopefully it made a little bit of sense. Optimization's a little crazy, I know, but if you see it, there should be some interesting problems if you see it on the AP exam. All right, email me, let me know what I can do to help.